Hello, it's me, and I wanted to go through the second part of this very elusive and fascinating concept of parity. Now, we described in the first part that parity just refers to the types of permutations, even or odd, that can happen, and every puzzle has some sort of a parity with it. We use the example of the game with the cups to show that if I limit myself to certain types of moves, then there's certain ones that are legal and, quote, illegal in order to get to a solved state. So with this puzzle the way it is, you can only move a total number of even number swaps. So because of that, I could never swap these two because that's just one swap. It has to be an even number. Now I could do an odd number of, say, edges as long as the total amount of swaps is going to be an even number. So an example of that, certain impossible states you'll never get. So when solving these puzzles, you might run across situations that appear to be impossible, and it's important to understand when we're dealing with actual parity problem, which has to do with reducing something into an impossible state from even to odd, or if it's just kind of a false equivocation. So one impossible state is, say, having two that are flipped and everything else is fine, because you only have one swapped, and you can't have an odd number swapped. So that would be impossible if, say, these two were flipped. So if you saw those two flipped over there. And I gave you the example of how when I turn this, it's kind of like the corners three cycled, 1, 2, 3, but then the edges also went 1, 2, 3, so that's a total of 6. So you can do that, that's fine as long as the total amount is even. Another impossible state is just one is flipped. Because again, that's going to be an odd number. Another impossible state is if this is flipped, if just the corner is flipped but nothing else. So I think we went over that. Now, when we see an apparent impossible situation with an even layer puzzle, I don't really think of that as a parity problem. We recognize that something is strange with that shouldn't happen in terms of the parity, but it's really just because of a placement. And I gave an example of this guy over here when we falsely equivocated this in one rotation when it should have been another rotation. But there's some other examples that are worth going through to ask the question, is it parity or is it false equivocation? So let's take a look at something that you might have remembered from previous. We have a void cube. Some people ask some good questions about this. What do you make of this? Well, this appears to be an impossible situation. Everything seems to be in. Our edges are where they should be in correlation with each other. But we have this situation here where this needs to flip-flop with this. This gray one needs to come here, this black one needs to come here, and I kind of set it up to where everything is in except for these two. So this is an impossible situation because you have to swap these two. So what do I make of this? Well, anytime you see a problem where there appears to be a parity problem with the corners, I know that there's an issue because you never reduce corners. Corners are always the ultimate calibrator of any puzzle, because as you keep expanding things out, it's the edges and the centers that ultimately need to be reduced. So when I see this, the first thing I ask is, well, do we have false equivalency? Do I have another corner that looks just like this that is somewhere else too? And the answer is, well, no, this is otherwise standard. So when I see this, I know that the problem must be somewhere else, some other equivalency. Well, what can falsely equivocate in this puzzle? And the answer is these empty sets. We're actually falsely equivocating one empty set for another. So the technique that I use to do this is always, when in doubt, get your corners oriented correctly. The way to do that is I need all of them out, one of them in, or all of them in. I can't have two in, so I would just kind of move this to the side, any one of these in. This one is in, and that's pretty much it. So if that's in, then I'm just going to set everything else up. Bang, bang, zoom, zoom, pow, pow. I'm just doing a corner permutation, because if one is in, then I can three cycle the rest. And the total amount of swaps are 1, 2. So that's basically an odd number, so we're doing okay with that. An even number, rather, so we're doing okay with this. So this is where it needs to be, this is where it needs to be, as is this, as is this. So let's go ahead and flip these back in now just to help illustrate where we're at with things. Okay, so when we look at it like this, this is appropriate. Now what about these edges? So we have to permute these guys. So I just kind of reconfigured it, which just basically took that to this configuration here where I have to swap these two edges. So what I'm going to do is recognize that I put these in wrong, and I want to make it into a situation where one of the edges are correct. And I'm going to say that this, which was my red edge, my blue center actually, is actually my red center, red empty set, and that's going to come over here. So what I'm going to do is by moving it down here, this now is the only one that's correct. Because red is here, blue is here, it's just flipped. The rest are incorrect, so that allows me to do a proper amount of exchanging, 1 and then 2. So that's exactly what I'm going to do. I'm going to assume that this is supposed to be my red center here. Not here, but here. I falsely equivocated a completely empty set here and put it here. No parity algorithms or issues are going to happen. It's just a question of reconfiguring. So how am I going to do that? Well, what I'm going to do is I'm going to move this down here, go 1, 2, move it back up, and go 1, 2. Why did I do that? I did that because now this is my new red center, and I had to get this red here and this red here. So what I did is, notice when I moved those, I ended up doing an even number of swaps. That even number of swaps put things back in. Now it's just a question of moving these where they're supposed to be. So I'm going to just use regular algorithms to take this and turn it around. So I'm going to move this up here and turn it around. And my reason for showing this, which I've already shown in previous tutorials, so it's over here now, is that all I'm doing is I'm just reconfiguring. I'm using the same laws of the cube. In other words, I can find my way through this by using all the accepted laws. And what appeared to be parity was nothing of the sort. What appeared to be parity was just placement issues. And I'm not doing anything fancy or anything different than the proper number of even exchanges on a 3-layer puzzle. So now this is going to turn around. So really what I did is I let my edges calibrate the puzzle to show me which is supposed to be the correct place, and then I was able to put things back in. And now I just solve it accordingly. F, R, U, R, I, U, I, F, I. There's my L, F, R, U, R, I, U, I, F, I, F, R, U, R, I, U, I, Fi, so all these are in. So now this puzzle should be properly calibrated. So by recognizing this and recognizing the difference, I can seek out where the problem was. Okay, so let's pick up that concept again. We're going to move into the notion of supercube parity and what you can and can't do in terms of center orientation. Rotation of the center is going to be important when it comes to supercube, and when what are the things that are impossible and what are the things possible, because when I translate this to a 4x4 supercube, I'm going to be reducing the centers, and the reduction of these centers are going to be important in terms of proper placement. So what you can do is you can rotate 1 by 180 degrees. Why? Because you're doing 2 moves. 1, 2. But you can't rotate it just 90 degrees because that's equivalent of 1 swap. Instead of 2 swaps, it's 1 swap. But you can rotate 190 degrees and another 90 degrees. So if you find yourself in a situation where there's just one that's 90 degrees, but not another one, that is a parity problem. That shouldn't happen. That's actually an impossibility. And you can try that. Let's try swapping these two. Okay, and once doing that, you can see everything about this is fine except this is rotated 180 degrees. You see the white stripe is down and the yellow stripe is up, and this is rotated here too. So you can see I have not broken any parity here. What you would also see is that I can have this 90 degrees if I have this 90 degrees, and that can be solved that way too. But you'll find you can never have it 90 degrees. So with that said, I'm going to bring up another parity situation that happens with 4x4 mods. Now, you don't get it with this kind of a mod, but you will get it with these. Now, can you see the difference between this one and this one? This is the megamorphings. This is the octahedron, the 4x4 octahedron. I'm going to use this one because this one is more mass-produced. This one's a little harder to get. The difference is that every one of these centers is unique, white and blue, so they all have 2 colors. Here, I have centers that are not so unique. They're shared between 3 different places. Same thing here, I've got a center here that's the same color as a center here and here. Because of that, I have the potential of having a very curious and interesting parity that happens with that. So let's say you're doing this puzzle and you've got it up to here, you've got all the centers in, and you've reduced the edges and everything, and now you're getting ready for the corners. So you want to put the corners in the right place. So none of them are where they need to be. So you're going to go ahead and you're going to do the algorithm to rotate them around. So bang, 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 zoom, zoom, pow, and splat. See where you're at? Nope, nothing yet. Okay. Turn, 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 turn. And you notice something curious. This is in, but these two aren't. And you know from what you understand about parity is that this is an impossible situation. To solve this as a 3 by 3, you cannot have 2 that are out and 2 that are in, because it would mean that you're going to do an odd number of swaps, and you can't do that. So then you're thinking naturally, well, maybe I falsely equivocated. Is there another triangle, white or green? And the answer is nope, not that. So then you realize that there must have been an issue truly with parity, but with what? Never the corners. How about the edges? Well, no, if there was parity with the edges, that would manifest itself as 3 up and 1 down, 1 turned upside down, because then that would have to be a turning 1. That was one of those impossible situations that I mentioned over here. But that's not how this is manifested. So therefore, it must be in how we placed the centers. So my suggestion, if you get to this situation, is you have to exalt the corners. Forget about everything you just did and put the corners back. And the way that you do that is you have to set it up to where all of the corners are in, none of them are in, or one of them is in. So if I move it like this, and I just look at the corners in conjunction with the bottom here, this isn't over here, not in here, not in here, not in here. So I'm going to hold it like this and just get these little bitty corners in, and then we'll have to coordinate everything else, the center, in other words, based on that. So, because if 1 is in, then permuting these 3 around is like doing an even number of swaps. So these will swap here, 1, and then these will swap here, 2. So that way you know that you can do a 3 cycle with these. You're moving an odd number of pieces, but you're swapping even number of pieces. So bang, bang, zoom, zoom, pow, pow, crack, splat. And keep going once more. And turn. Okay, so this is correct, this is correct, this is correct, and this is correct. So now what we're going to do is let's go ahead and put these in relationship to the corners, just to kind of prove a point. Now, again, I kind of did that to get it in this configuration. Again, it's not meant to be a tutorial. I just want to demonstrate a point, how all these corners are in, all these edges are in. But look what happened with the center. What you can see is that this center is actually rotated 90 degrees, and it's the only one that did that. And this is where the true parity of that situation with the corners comes out. That true parity is basically a 90-degree rotation. This needs to be here, this needs to be here, this needs to be here, this needs to be here. This is rotated 90 degrees. We know that that's impossible, which means that situation is a true parity. Not a parity of corners. We don't get that. It's a parity of the center. And that happened because you put it in wrong. You put it in that situation. Now, when you look at the tutorial of this and this, I have that situation. So the way to do this, and you could have skipped the whole step of putting these edges in. You didn't really have to do that. I just wanted to show how this is an impossibility and this is a different kind of a parity. But the way that you get out of this is that you have to go into your reduction. Remember how we, with a 4x4, when we had that parity, we had to go into our reducted edge and do algorithms, in that case the Red Bull algorithm, to get out of it? Well, we have to dive into the center that we reduced, unreduce it, and then put it in correctly. The good news is we have kind of an easy way of doing that. First off, I'm going to use the triangles, these little edges, as my guide is what's supposed to go where. Like this green is supposed to go over here. Plus, I do have the fact that I have other areas, like this green can correlate with this white can correlate with this. So I do have other areas that I can use to sort of do an even exchange. It's not a false equivocation, but it can take a 2 cycle where you're swapping 1 and make it into a 3 cycle where you're swapping 3. Well, you're doing a total of 2 swaps, although you're cycling 3. So the way that I would get out of this is I'm just going to move this up here and then move it down here, because I'm going to take this green and bring it to here. The overall result of that is I'm going to do it twice. Once and twice, because of that algorithm that can bring this to here and this to this to here, this to here, and this to here. Do it twice and this will end up here, this red will end up here, and this orange will end up here. So forward, bang, bang, zoom, zoom, pow, splat. Okay, and then move this back here. So now I know this green is now going to move to where it's supposed to be. Back. The good thing about these algorithms is I'm not going to mess up my reduced edges. This always stays the same. I'll move this back up here. The only thing that's changed now is this is cycling, these stay the same, but now I've got the green where it's supposed to be. And now this red is ready to go where it's supposed to be, which is down over here. So I'm just going to move this like so. What that's going to do now is in 2 moves, see, I could move it here and this will come down here in 1 move, but I don't want to bump this green out. I already put that green in, so I don't want to do that. I'll move it over here. So in 2 moves, this red will end up here, this yellow will end up here, and this white will end up here, ready to be lodged into here. So, do it again. Bang, bang, zoom, zoom, pow, splat, and move it back over here. And now do it once more. So this is where it's supposed to be here. The red is supposed to be here, and I can actually move it over here and see that that's the case. The yellow is here, now I got to put the white one here. How am I going to do that? Well, this white has to make it down here, this orange has to make it over here. So what I'm going to do is cheat a little bit. I'm going to move this here, because I know that this is supposed to come up over here, so that'll be no problem. But this green is going to move over, which you might think is a problem, but I'm going to use this to my advantage. So let's move this up here. Okay, so now all of these should be in up on this side, but what about down over here? What I have is I have to flip these two. This is where it needs to be, this is where it needs to be, this green has to come here, this white has to come over here. So what I can actually do is I can make it look like it's a 3 cycle. I'm going to move this green over here, and if I move it once, this white will be here, this green will be here, and this green will be here. So it's like I 2 cycled this, and I haven't done anything with this green. Bang, zoom, pow. Okay, the end result should be all of these are fine, and now all of these are fine. So I've now reset the centers. The edges kind of came out, but they're still reduced properly. So what I'm going to do is I've recalibrated the puzzle, and now I'm going to go back. Now the way that you avoid this from happening is before you finish the last center, put the corners in to see exactly where it's supposed to be. But now, as you will see, just put this corner in here. I pretty much recalibrated this to a point where it should work. It should work well. So this is going to come down here. So this is calibrated back here. Now the question is, did it work? Well, we put all these guys in first. This is upside down, as you can see here. This is upside down, this is right side up, and this is right side up. So these two are right side up, and we have ourselves an L formation. So F, R, U, R, I, U, I, F, I. Okay, then this should be a line, F, R, U, R, I, U, I, F, I. So everything should be up over here. So what I'm going to do is position my centers appropriately, and now I have one edge in place, the rest are not, which does not break the parity of this puzzle. I can do even exchanges here, R, U, R, I, U, R, to U, R, I. Everything is fine here, and look at my corners. Well, I have one in and I have three out, so now it's been recalibrated. So forward, back, bang, bang, zoom, zoom, and it's done. And the reason why that worked, and again, I went through that fast, but this was more to illustrate parity in what I did. I do have a tutorial on how to solve this. What I did is kind of a quick version of that. Now, normally I wouldn't let myself walk into that trap, because just before getting this center, I would have put in my corners already to decide what's supposed to go where. But to those that have two that are flipped, understand you put that in wrong, and you're just going to have to use the same algorithms to get the corners where they should be in conjunction with everything except the center, and then from there position the center and put it in so that it matches with the corners over there. So that is basically how to approach Supercube type parities and how to recognize it, because with Supercubes the orientation of the center matters, and it was important to go through what's allowed in terms of the orientation, what's not allowed. You can have two exchanges, two rotations, an even number rotation, not an odd number rotation. So that's how to recognize that it was not false equivocation. In this case it was false equivocation and not so much a parity problem, because I just used repositioning and standard even permutations in order to solve it. With this, I recognize that I did a problem with the process of reduction. It was a parity problem. I had to dive into and destroy my reductive function and then put it in another way. So that's how to recognize things as a supercube. Next, more examples. Thanks for watching.